In the next segment, we will delve into other geological phenomena that shape our world and explore the intricate connections between Earth's interior processes and the surface features we observe. Earthquakes are natural phenomena that result from the sudden release of energy stored in Earth's crust, causing the ground to shake. They can cause widespread destruction, impacting millions of lives and resulting in significant economic losses. Understanding the causes of earthquakes and their role in Earth's geological processes is essential for better earthquake prediction, mitigation, and response. Earthquakes are primarily caused by the movement of Earth's tectonic plates. As these massive plates interact with one another, stress builds up along their boundaries, which are also known as faults. Eventually, this stress is released in the form of an earthquake, causing the ground to shake. The movement of tectonic plates is a continuous process, which is why earthquakes are a natural part of Earth's geological processes, shaping and reshaping the planet's surface over time. Tectonic activity is the primary cause of earthquakes. This occurs at the boundaries of Earth's tectonic plates, where stress builds up along faults. When the stress reaches a critical level, it is released in the form of an earthquake, causing the ground to shake. The movement of tectonic plates is a continuous process, leading to earthquakes of varying magnitudes worldwide. Volcanic activity is another cause of earthquakes. As magma moves and pressure builds beneath the Earth's surface, it can trigger seismic events. Earthquakes are often associated with volcanic eruptions, as the movement of magma can cause the ground to shake, signaling an impending eruption. In some cases, earthquakes can also cause the collapse of underground magma chambers, leading to volcanic activity. Human-induced earthquakes are seismic events caused by human activities, such as mining, reservoirs, and fracking. The extraction of resources, impoundment of water, and injection of fluids into the Earth's crust can alter stress conditions and trigger earthquakes. While these events are typically smaller in magnitude than natural earthquakes, they can still cause significant damage and pose a risk to public safety. Primary P waves are the fastest type of seismic waves, traveling through the Earth's layers at speeds ranging from about 4 to 8 kilometers per second. These waves are also called compressional waves, as they cause the ground to move back and forth in the same direction as the wave. P waves can travel through both solid and liquid layers of the Earth, including the planet's outer and inner core. Secondary S waves are slower than P waves, with speeds typically between 2 and 5 kilometers per second. They are also known as shear waves, as they cause the ground to move perpendicular to the direction of the wave. S waves can only travel through solid materials, which means they cannot pass through Earth's liquid outer core, creating a shadow zone on the opposite side of the planet. Surface waves are the slowest seismic waves, but they often cause the most damage due to their long wavelengths and high amplitudes. There are two types of surface waves: Rayleigh waves and love waves. Rayleigh waves cause the ground to move in an elliptical motion, similar to ocean waves, while love waves generate horizontal shearing motion. Both types of surface waves can cause significant damage to structures and infrastructure, especially during large earthquakes. Ground shaking is the most noticeable effect of earthquakes and can cause significant damage to infrastructure and buildings. Depending on the intensity of the shaking, structures may collapse or suffer from extensive cracks and deformations. Additionally, ground shaking can trigger secondary hazards, such as landslides and avalanches, which can cause further damage and endanger lives. Tsunamis are giant waves generated by earthquakes, particularly those occurring beneath the ocean floor. When a powerful earthquake displaces a large volume of water, it creates a series of waves that can travel vast distances across the ocean. These waves can grow in size as they approach the shore, inundating coastal areas and causing massive destruction. Some notable examples of catastrophic tsunamis include the 2004 Indian Ocean tsunami and the 2011 Japan tsunami, which claimed hundreds of thousands of lives and caused immense damage. Ground rupture occurs when an earthquake causes visible displacement of the Earth's surface along a fault line. This can result in significant damage to infrastructure, such as roads, pipelines, and buildings, as well as changes in land use patterns. In some cases, ground rupture can create new landforms or alter existing ones, impacting ecosystems and human settlements. Understanding the potential for ground rupture is essential for planning and designing infrastructure in earthquake-prone areas. Seismographs are instruments designed to detect and record seismic waves generated by earthquakes. They help scientists measure and analyze the strength and characteristics of these events. There are several scales used to quantify the size and impact of earthquakes, including the Richter scale, moment magnitude scale, and modified Mercalli intensity scale. The Richter scale and moment magnitude scale focus on the energy released during an earthquake, while the modified Mercalli intensity scale measures the perceived shaking and damage caused by an earthquake at specific locations. Earthquake prediction and monitoring involve the use of seismic networks and early warning systems to detect and analyze seismic events in real time. These systems aim to provide advanced notice of potential earthquakes, allowing for evacuations and other emergency measures to be put in place to minimize the impact on lives and property. However, accurate earthquake forecasting remains a significant challenge, as the processes governing when and where earthquakes will occur are highly complex and not yet fully understood. Despite these challenges, progress continues to be made in understanding the underlying mechanisms of earthquakes, improving monitoring techniques, and refining early warning systems. Building codes and earthquake-resistant structures play a crucial role in minimizing the damage caused by earthquakes. By using techniques and materials designed to withstand seismic forces, engineers can create structures that are more resilient to ground shaking. These approaches may include base isolation, energy-absorbing dampers, or reinforced concrete and steel framing. Adherence to building standards and regular inspections are vital to ensuring that structures maintain their integrity and provide safety during an earthquake. Emergency response and preparedness are essential components of reducing the impacts of earthquakes. Earthquake drills and public awareness campaigns help educate individuals and communities about the necessary actions to take before, during, and after an earthquake. These measures may include developing an emergency plan, assembling a disaster supply kit, and practicing drop, cover, and hold-on techniques. The importance of individual and community readiness cannot be overstated, as it can significantly affect the overall response to and recovery from an earthquake event. The role of science in earthquake risk management cannot be overstated. Through ongoing research and innovation, scientists continue to advance our understanding of earthquake processes and develop new techniques for monitoring seismic activity, predicting earthquakes, and designing earthquake-resistant structures. This knowledge is invaluable in helping us prepare for and respond to the inevitable seismic events that will continue to shape our planet's landscape and impact our lives. In this segment, we'll explore recent advancements in earthquake science and technology. First, let's discuss innovations in earthquake monitoring and detection. Scientists are now using advanced seismometers and sensors that can detect even the slightest ground movements. These instruments allow for more accurate data collection and analysis, ultimately helping to improve our understanding of earthquake processes. Another significant development is the use of remote sensing and satellite-based technologies. These tools can monitor Earth's surface deformation from space, offering a broader perspective and more comprehensive data for researchers to analyze. Now, let's turn our attention to developments in earthquake-resistant design and materials. Engineers and architects are constantly working on smart materials and technologies to reinforce buildings and infrastructure. These materials have properties that allow them to adapt and respond to external forces, like those experienced during an earthquake. Lastly, let's talk about innovations in base isolation and damping systems. Base isolation involves separating a building's foundation from the ground, reducing the transmission of seismic forces. Damping systems, on the other hand, help to dissipate seismic energy, minimizing the vibrations experienced by the structure. Both of these techniques have proven effective in enhancing the resilience of buildings and infrastructure during earthquakes. In this segment, we'll delve into some notable case studies of major earthquakes throughout history and examine the lessons learned from these events. First, let's take a look at the San Francisco earthquake of 1906. This devastating quake, which measured an estimated 7.9 on the moment magnitude scale, resulted in widespread destruction, fires, and the loss of over 3,000 lives. The disaster highlighted the importance of understanding seismic activity and implementing building codes and emergency response measures. Next, we have the Great Alaska Earthquake of 1964. This 9.2 magnitude quake remains the second largest ever recorded, causing extensive damage and triggering tsunamis that impacted coastlines as far away as California and Hawaii. The event demonstrated the far-reaching effects of powerful earthquakes and underscored the need for effective warning systems and preparedness measures. Now, let's discuss more recent earthquakes, starting with the 2010 Haiti earthquake. This catastrophic 7.0 magnitude event resulted in the deaths of an estimated 230,000 people and widespread destruction. The earthquake exposed weaknesses in infrastructure, lack of preparedness, and inadequate building codes, emphasizing the importance of proactive measures to mitigate earthquake risks. Lastly, we'll examine the Nepal earthquake of 2015. With a magnitude of 7.8, this quake caused significant damage to buildings, infrastructure, and cultural heritage sites. The event highlighted the need for international collaboration in disaster response, improved building codes, and the importance of preserving historical structures through earthquake-resistant techniques.